the technique that I just demonstrated, separation of variables, only works when the differential equation is separable. So a differential equation, dy dt equals f of t and y of t, is separable if the right-hand side, f of t, y of t, is the product of two functions, a function of t and a function of y. We'll use, say, k of y. Then I can rewrite the equation dy dt is equal to g of t times k of y. Now, it's going to be a little bit easier for me to describe this technique if I think about f of t and y of t as being the quotient of two functions. We'll call it g of t over h of y. So in this case, k of y is actually equal to 1 over h of y. So it's just another way to write it. And that way I can rewrite this equation as dy dt equals g of t over h of y. So what I'm going to do is I'm going to proceed like I did before. I'm going to separate the variables. Okay, so I'm going to write this as h of y times dy dt, so all the y's are on one side, and I'm going to set that equal to g of t. Now, the thing is here, I'm not going to multiply by dt because you can't actually multiply by dt because dy dt is not a fraction, right? It's a derivative that's defined by a limit, okay? But I'm going to show you why the shorthand kind of works. I'm going to look at the left-hand side and I'm going to realize that it kind of looks like the chain rule, okay? So h of y dy dt kind of looks like the result of a chain rule. It looks like I took the derivative d dt of, say, some function capital H of y, where the derivative of capital H is lowercase h. Okay, so just kind of as a side computation, okay, we're going to say that d dt of capital H of y is equal to, the derivative of capital H is going to be lowercase h of y times dy dt. Okay, so we're thinking about capital H as being the antiderivative of lowercase h. Okay, so what's on the left-hand side is really like a chain rule. Okay, and so we have the time derivative of that is equal to g of t. And so now what I can do is I can integrate both sides with respect to t. So now I can write this as the integral of d dt h of y dt is equal to the integral of g of t dt. And then the left-hand side is h of y, because the integral of the derivative, okay, is just going to be the function itself. So it's the antiderivative h of y. And we're saying that h of y is equal to the integral of g of t dt. Okay, but what is capital H of y? Capital H of y is the antiderivative of lowercase h, okay, dy. So we're saying that the antiderivative of h of y dy is equal to the antiderivative g of t dt. And so now you can see why I could kind of multiply by the dt. Okay? And so I can do that on both sides. What's important to understand, though, is that once I am able to integrate the left-hand side to get capital H, that last step to solve for y requires me to have an inverse for h. I will have to be able to solve for y, because y is going to be the inverse of h times the antiderivative of g of t dt. And so this makes the technique of separation of variables very limited in its application, because I'm only going to be able to solve for y in certain nice cases. And in many of those cases, it's going to be an important application, like the Torricelli's law that you saw previously. And so it is applicable, but it's not going to work in every case. So that gives you an understanding a little bit of how the separation of variables technique works. Okay, so now I'm going to move on, and I'm going to do a few examples of separation of variables. So let's start with dz dt equals minus t times z, and z of 1 is equal to 1. Okay, so I'm going to separate the variables. I'm going to write this as dz over z equals minus t dt. And there's two ways I can proceed. I can do this as a definite integral or as an indefinite integral, a lot like when we were dealing with the integrating factors. So today, for this example, I'm going to do this as an indefinite integral. So I'm going to say that the antiderivative dz over z is going to equal antiderivative t dt. So then we're going to get the antiderivative of 1 over z is natural log of z. But it's not the natural log of just z, it's actually the natural log of the absolute value of z. So if you remember back to calculus, hopefully, when you were looking at antiderivatives of 1 over t, or 1 over z, in this case, that you learned that actually it's the natural log of the absolute value of z. And these absolute values are important. Okay, so this is going to equal minus 1/2 t squared. And I'm going to add a plus c. Now at this point, I'm going to put in the initial condition, because it's going to be the easiest point at which I'm going to be able to solve for c. So I'm going to get that the natural log of 1 is equal to minus 1/2 times 1 squared plus c. So in this case, the natural log of 1 is 0. So c is going to equal 1/2. Okay, that's going to give me my constant, c. Okay, so I have the natural log of the absolute value of z is going to equal minus 1/2 t squared plus 1/2. And now I need to solve for z. Luckily, there is an inverse function, so I can do e to both sides, so that the absolute value of z is equal to e to the minus 1/2 t squared plus 1/2. And then I need to decide whether the absolute value of z there is supposed to be positive or negative. I want to match the initial condition. Z of 1 is equal to 1. So z of 1 is supposed to equal e to the minus 1/2 plus 1/2. That's e to the 0, which is 1. So that means that I need the positive from the absolute value. Okay, so it could have been that z of t was plus or minus e to the minus 1/2 t squared plus 1/2. But to match the initial condition, I now know it must be the positive one. And so now we've solved this differential equation using separation of variables. Okay, let's move on to the next example. This one is dy dx is e to the x minus y. And at first glance, this does not look like it's a separable equation. But if we remember our exponential rules, dy dx is equal to e to the x times e to the y, e to the minus y. And so we can separate this, and we can write this as e to the y dy by multiplying both sides by e to the y is equal to e to the x dx. Okay, this time I'm going to do these as definite integrals, just to do something different. Okay, so I'm going to do the integral of both sides. So I'm going to integrate from the starting y, which is 2, to y. And I'll integrate e to the, I'm going to need another letter. So I'll go with w, dw. And then I'm going to integrate the other side, starting at x equals 0 and going to x. And I'm going to integrate e to the, let's use z, dz. Okay, so the antiderivative of e to the w is going to be e to the w, and the antiderivative of e to the z is going to be e to the z. And so let's see, I'm going to get e to the y minus e squared is equal to e to the x minus e to the 0. So that tells me that e to the y is going to equal, let's see, e to the x plus e squared minus 1. And y, in this case, if I solve for y, is going to be the natural log of e to the x plus e squared minus 1. So you'll see that it's not necessary to solve for a constant, which is why I like to solve the problem this way using definite integrals. Now, I do want to point out I could have done it as the antiderivative of e to the y dy equals the antiderivative of e to the x dx, in which case I would have gotten e to the y equals e to the x, and it's important to add a plus c. Now you could add a plus c to both sides, but then those two constants could be combined into one. So I always just add a plus c to the other side if I solve the equation that way. And if you don't add the plus c, you can have a lot of mistakes. So it's important to make sure you add the plus c. In that case, you'll see that y is equal to y is equal to natural log of e to the x plus c, and then you'll have to solve for the constant c, which you should see will end up being e squared minus 1. So this is just an alternative way to do this. Okay, so let's move on to one last example. Okay, dy dt is equal to t over y. And I'm going to separate the variables. I can see that I can do y dy is equal to t dt. I'm going to go ahead and do this using indefinite integrals again. So I can think about this as being the antiderivative of y dy equals antiderivative of t dt. So 1/2 y squared is equal to 1/2 t squared plus a constant. So y squared is equal to t squared plus 2 times c. But we don't know what the arbitrary constant is yet. So 2 times a constant is the same thing as a constant. So I might as well just write that it's another constant. I'll even give it a different name, call it d. So now I can look at my initial condition. And it's a good time to do it now because it's easy to solve for d now. Okay, so I'm going to get that negative 2 squared is equal to 1 squared plus d. Okay, so d in this case is 3. Okay, so I have that y squared is equal to t squared plus 3. Okay, so I'm going to take the square root of both sides. So y is equal to the square root of t squared plus 3. But it's important to understand in this case that there are 2 possible square roots. Okay, there's a positive square root and a negative square root. So I have to figure out which one is the correct one. Okay, so if I use the initial condition again, y of 1 is going to be plus or minus the square root of, let's see, 1 squared plus 3. So that looks like plus or minus 2. And so I need the initial condition to match negative 2. So I'm going to have that y of t needs to be the negative square root of t squared plus 3 so that it matches the initial condition. Okay, so again, there's another part where we could have an error with this method, okay, because I need to decide whether it's the positive or the negative square root. And so it's important that I go back to the initial condition and I make sure that it matches.